put on place for all of posterity's sake. Okay, let's look at who do we have here in the chat. Who's getting on our costume contest? Whew. All right, I'm gonna put that back on when we start lecturing for real. But for now, okay. So we've got Mark coming in as a giraffe. It's looking like endangered species for the win.
Oh yeah.
We got Vivek, who's got his own special data science jitsus. Tammy, does yours count as a costume?
Like a person with in-person graduation. That's the costume.
Oh,
like I'm having in-person graduation. Like I'm throwing the cap. Like what a concept.
That is okay. Wow, that one hurts actually. That one I'm feeling that one. Someone who had a slideshow graduation last spring. I feel that vividly. Okay, Isabel, I see we're seeing Trader Joe's. Is that, are you or have you legit worked at Trader Joe's? You just got the swag?
No, I have the sweatshirt for no real reason. So
that's pretty baller.
Yeah, it's kind of swaggy.
Okay, Brendan, are you like, is that your avatar, or are you legit just sitting still? Like what's going on there? He has mastered the art of completely freezing. It's like one of those statues, human statues in the park. Implacable. Okay, Akshay, looks like you broke out your old cap and gown. Also feeling a little graduation.
Yeah, it has the
nostalgic.
UCLA 23 on it. So not a graduation nostalgic. I'm a UCLA grad. That's what I'm dressed up as. Because this data science class is gonna get me to drop out early and get out. I don't know. I'm kind of messing up, but yeah.
Gonna make
Akshay's converting to the dark side real quick. Give him a second.
Okay.
Me and Brandon have like a bit of a duo picture going on.
I'm seeing. Okay, wow, this is interesting. A team contest. So costume. I have not seen that before. Okay.
Give Akshay a couple of seconds. He will join the team too.
Okay, Akshay's getting on that, and then Timothy, did we? Your quarantine field enchantment. That is
this is always my picture. I changed it like way back in like last spring when we all had to go into quarantine, and I was like, what would be a good profile picture? And it was just quarantine field. It's not really okay.
Run with it. Literally, the person who won last quarter, her avatar was a can of soup, and I think people as a joke just started voting for it, and it just kind of took off and became so. Go for it. Okay. Anyone else getting in on this?
Vote for the black box.
The black box. The man, Godfried is the man of mystery. Team contest. I feel like you can totally do team costume. I mean, that's awesome coordinating it. Okay, but now we have to bring some semblance to this chaos. We have to vote on this. So I have my poll. Where's my poll? Okay, so we got to assign things. So hop in the chat. We're gonna do. Let me see what my polling is. Okay, A through F, and let's just hope. Well, let's see how many people we've got here. That may not be enough people. Let's see. Do I have to edit it? I really hope I can edit it because I feel like we've got more. Okay, cool. I'm just going to add more options. I'm just going to add letters. G. Okay, I think that's going to cover everybody. Okay, then. Be it. Okay, can I save it? Okay, so in a moment I will take the poll live. What I need you guys to do is assign. So on the chat, put your name and your costume and assign yourself a number from A to I that has not been chosen yet. So like, I'm not gonna, okay, good. Vivek in. So A is going to be Vivek. I is going to be Isabel. Okay. Y'all just couldn't be sequential. You just had to be difficult about this, huh? Okay. Thank you, Brandon, for doing it sequentially. You guys are killing me with these choices. Everyone's just going to vote for C then. Okay, never mind. Somebody chose C. You choose the one that like nobody has voted for. Okay, so we've got what's been assigned so far. We have A, I, F, B, C, D. Okay, so I think we still got E. I think we still have G. I think we still got H out there. If somebody wants to grab that. Okay, Akshay grabbed the H. Timothy, you got to assign. Have you assigned yourself yet? You have to assign it because we're going to do this just to vote rather than put all your names. And I just have like a poll that's going to be who won today's contest, and then just the letters A through I. So you have to choose a letter. All right, guys, poll's going live. Last chance. Okay, launching poll now. May the best data sciencer win. Okay, 60% voting. 63, 66, okay. Hitting the 2/3 mark. Awesome. Let's see, do we got some, oh, it's a tight race here. I'm seeing, I gotta keep track of who's who. Okay, it might come down to the wire on this one. Okay, let's see. It's looking like Naruto and who's the F? And Tammy. Neck to neck. 80% of the vote in. Those of you who haven't voted, now is the time. 83. Oh, F's pulling ahead. She tugged on our heartstrings. Made us nostalgic for the good old days where we could catch germs from each other and cough on each other. That fear of social stigma. You know what they say, the friends that germ together. I don't know what would rhyme with that, but. Okay, 88% of the vote. Vote now or forever hold your peace. You know, I said we were going to give out 2 awards here. I'm seeing a problem here. We have 2 people tied for second place. We got A and C tied for second place. Who's A? So somebody needs to vote and break the darn tie. It's between the endangered giraffe and Naruto. Okay, going once, going twice. Poll closed. Okay. And in first place, we have Tammy with the win. And we have a tie for second place between between the hidden leaf shinobi and the endangered giraffe. All right, awesome, guys. Send me your emails. This friendly neighborhood Spider-Man be paying his dues. All right, now we're going back to work. The mask is coming back on. It's work time. Time to get serious. All right, let me share my screen. Okay, awesome. And share. Okay, where is this thing? Okay. All right, just a non sequitur, but did want to get this out of the way because I have been getting a few questions about this. And I will neither confirm nor deny that this is the case, but it is useful. So today's lecture, I kind of wanted to take a little bit of a step back because we're done with homework 2, done with project 2. We probably nobody has realistically looked at project 3 yet, but sort of leading into our conversation, particularly when we get into like neural nets, and we're going to spend a lot of time focusing on things like backpropagation and vanishing gradients and loss functions. And so there's like a lot that we're going to be talking about around that. And I just kind of want to get those core concepts down. So I wanted to spend today talking about the concept of learning and machine learning. And again, my hope is to kind of just give you guys kind of that foundational understanding of it so that when we get into those concepts like vanishing gradients, exploding gradients, like you're going to have a base to be like, oh, okay, I know why we're talking about that and what that is. So kind of taking a step back with that, you know, okay, I got to take this mask off. This is too itchy. Ugh, I tried. I can fight crime and I can teach data science, but darn it, I cannot do both. So remember, we've sort of mentioned this last time. When we talk about classification models, we have said that in most instances, our model kind of learns something about our data. It takes the training data and it uses it to learn something about the data. And then based on what it's learned, either it's sort of created in the case of like an SVM or a KNN, like it's learned a decision boundary, or in the case of something like a logistic classifier, it's learned sort of an odds ratio for probabilities. It then sort of applies a decision function. It then kind of takes that information and uses it to come up with a classification. And so, you know, we've already kind of talked a little bit about sort of how you can manipulate that decision function to impact the results and performance of your model. So I don't know if you guys kind of remember that now, but just kind of really quickly, what's kind of some manipulations you might want to do to a decision function for your model? Like what might impact the decision function? Okay. I feel like I'm like Dora the Explorer with this. It's like I talk at the screen and then pause dramatically. Okay, so good question. So penalty terms. So regularization, penalty terms. Yeah, great question. Is great thought. Those are really going to be for your loss function. So we're going to get into those today. The specific thing for your decision function that you could do is manipulate your thresholds for classification. And so just to kind of give you a specific example of this, if you care very much about, let's say, type 1 errors, precision. So you care very much about, you know, you don't necessarily need to get every actual positive out there in the universe, but you really want to make sure that if you get it right, you get it right. You might want to manipulate your decision function to have a very high probability threshold. You might say, you know, it's okay that I'm going to let a lot of true positives through and not classify them, but the ones that I do classify, I want to make sure I'm very confident about. Or vice versa, you might say, if you really care about type 2 errors, you know, if you want to make sure that you don't miss instances of a thing, then you might set your probability threshold very low and say, you know, even for items that have a relatively low probability, I'm still going to allow them through. I'm still going to make that classification decision because I just want to make sure I'm not missing any. And even if that means I make errors as a result and I allow, I make a number of false positive errors. That's okay, as long as I'm getting stuff in. So that's kind of a decision function. And again, when we talk about metrics for classification, the difference between like an accuracy, a precision, recall, and so forth, that's why you might want to manipulate a decision function based on that. So now we want to talk about that whole learning step and how it is that a machine learns, because we've thrown that word out there the whole quarter. We've been like, oh yeah, you learn a model of your data, and you never actually talked about what that means to do. So it's really going to come down to two things, and these are the two things I want to focus on today: loss functions, and then optimization and solver functions. So let's start with loss functions. We've already kind of touched on loss functions in this class. We've sort of had a little bit of introductions. This isn't the first time you're hearing about them, but hopefully we're going to kind of go into them in a little bit more detail at this point. So the loss function is essentially your machine learning scoreboard. It's how your learning model knows how it's doing. And generally speaking, a loss function is essentially monitoring sort of the amount of loss or the amount of error that's in your model. So you generally want a very low value for your loss function. The higher the number, the worse your model is doing. The lower the number, the better it's doing. So I mentioned that we have already seen these, and indeed we already have seen these. So you may remember this. We talked a lot about these around project 1 and sort of using sort of different loss functions for evaluating the performance of a regression model where you're making a prediction. So, if you're making a prediction, there isn't sort of an absolute right or wrong, but there's sort of a relative proximity that you have between your predicted value and the real value. And so we looked at a few approaches to those between like mean squared error, mean average error, and so on and so forth. And so if you remember these little graphs here where we have our real data, arrayed around here, and then we have kind of our regressionary line here, and then the error being sort of just the difference between predicted and actual. So that was how we handled regression. Classification approaches, we could do that too. We could just look at something like an MSE for classification as well, because if you think about it, let's use the example of a binary classifier. There's two discrete values, a 0 or 1, and then you'll have your predicted values, a 0 or 1. And where there is a difference between those, there is an associated error. And so you could theoretically just take the magnitude of that error. And sometimes people do that. But there's maybe a better way of thinking about the performance of a classification model. And generally, we don't tend to like to think about magnitude of errors. We tend to instead like to think about the associated probabilities associated with errors. And if you want kind of an intuition for why that is, let's kind of go back to ROC curves. Because if you remember, with an ROC curve, what we were looking at is we were saying like, how cleanly are we assigning these probabilities? How clean is our data? How sort of confident are we with the labels that we're assigning? Is it something that there's very clear, very discrete sort of probabilistic assessments for this, or is this data getting messy where there's kind of a lot of overlap in terms of the relative magnitude that we're assigning probabilities? And taking a step back, if you want to think about from a generalized term, the more confident you are and the higher the probabilities you assign to certain models, the more likely it is that that model will generalize well, because you're not just sort of thinking about how it does in that particular instance, but you're thinking at how well the model more generally does at generating probabilities that sort of correspond to the real world. So we're going to kind of think about classification loss functions in terms of a probabilistic approach. And we're going to build up to sort of the most common of these. Now, the one thing that I will just say across the board is that there are multiple different loss functions, just like there will be multiple different solvers and multiple different kind of approaches. I mean, there is, if you want to kind of ask like where the research in machine learning is, like what people are getting PhDs in these days, it's literally things like this, like coming up with alternative loss functions, coming up with different solver optimization approaches. Like a lot of the kind of the research that's being done today is being done specifically around this space. It's about kind of recognizing deficiencies or shortcomings in current models, either in terms of performance or computation, and trying to devise sort of alternative approaches. So let me just kind of start and say, like, there's a lot more than we're going to cover today. I'm just going to cover maybe the most obvious one or stuff that we've covered in class. So we're going to cover something called, ultimately, we're going to work our way to log loss, which is by far the most popular. To get there, we're going to talk about a concept called maximum likelihood estimation. So that's this idea, it's borrowed from statistics, which says that if you have data that sort of aligns to a particular distribution, we're going to try to figure out what parameters would have given us the highest probability of achieving that precise distribution that we see. So if you think about, that's almost the exact opposite of thinking about like a p-value. So remember, if you look at like a p-value of, let's say like a p-value of 0.05, right? What we're saying there is, what is the probability that the distribution that we're seeing could have happened given the null hypothesis, right? And so like that sort of critical threshold of 0.05 says, okay, less than 1 in 20 times this particular distribution could have occurred given the null hypothesis. And that's the point at which we say, okay, we can reject that in favor of the alternative. Here, we're kind of doing the exact opposite. We're saying, given this distribution, what is the particular sort of hypothesis that would have generated the highest probability of seeing precisely what we're looking at here? So that's what an MLE kind of looks at. And in this case, particularly, what we're looking at is we're saying, well, let's assume, given that we know the actual class values in our training data are 1 and 0, and so the associated real world probabilities of those are 1 and 0, let's look for sort of an MLE model that would minimize the difference between the actual probability distributions of 1 and 0 and the one that we get. And then this is kind of a key thing, because remember, we're not just looking to get it right. It's not just about ultimately making the right classification. It's about saying, can we get our confidence? Can we get our associated probabilities as close to the actual things as possible, as close to those zeros and ones as possible? And so the specific kind of measure that we look at to sort of look at sort of our hypothetical optimal probability distribution, which is, again, everything assigned to 0, 1 based on their actual level, versus our MLE that we're able to achieve, is this measure called cross entropy. And entropy in information theory terms is sort of the amount of kind of chaos or dissonance between different things. And so as you can imagine, what you're looking at here is the difference between those. You want something as similar, as little cross entropy as possible, because you want these to be as similar as possible. And then I just note here just a few kind of additional quick things that we do to get there, because as we mentioned with our loss functions, we want our loss function to be sort of a minimum, and so we're not looking at maximums. So to get into like a minimum format, we just take the negative of our likelihood estimator, and then we try to minimize it. It's basically the exact opposite of trying to maximize our likelihood estimation. We're taking the minimum of our negative thing. And then as a final step, for a variety of reasons, we then end up taking the log loss, both because that sort of changes the way we weigh our errors, and also from a computational standpoint, it significantly simplifies it by just taking the log of that. So that at a very high level is what log loss is. And then let's kind of look at sort of how that will perform by sort of doing it. So as I mentioned, it's not enough for us to get this right. It's not enough for us to kind of get the predictions right. We want to be as close to the actual values as possible. So we want, the best model is the one that is very confident and very accurate. Conversely, we want to make sure that we are not very confident and very wrong. And that's kind of what you see here. So this is a plot of the log loss, the penalty associated with the predicted probability. So in this case, if the actual probability is 1 and we have predicted 1, so our log loss there is 0, because again, we're trying to minimize that term, so that's perfect. And you'll see, because of the distribution here, All right, at 0.8, there's a small amount, but again, we're still doing okay. 0.6, it's still okay. 0.4, not great, but not terrible. Where we start to see this kind of exponential thing is as we get closer and closer to predicting 0, again, when it actually is 1, you see that the penalty for that becomes exponential. Because again, the idea here is we're not going to treat all errors the same. We're going to treat sort of when you are very confident and very wrong, we're going to punish that very heavily. So it's okay to be a little bit unconfident and still get it right. It's even okay to be a little bit unconfident and get it wrong. But we really don't want you to be very confident and wrong. And again, if you'll recall, that kind of weighing of different error types, we did the same thing with MSC. When we decided to square our errors there, it was the whole idea that there we were also applying this notion that said, we're generally more comfortable with small magnitude errors, even if there are many more of them, than a few very high magnitude errors, large magnitude errors. So again, this is kind of when we talk about the trade-offs and different sort of loss models that loss functions that you may choose, part of what you as budding data scientists working on your models would have to say is, okay, well, what kind of errors am I going to tolerate? What would I consider an optimal performance? Is it the kind of thing here where generally I want very confident models that tend to get things right, but I will disproportionately penalize confidence when it's wrong? Or generally, do I want something that maybe treats all errors the same, or as long as I get the right predicted thing, depending on how I set my threshold, it's okay if my probabilities are a little less confident. So again, one of the many tools in your toolbox that that you kind of as a data scientist will need to sort of determine when you're developing your own models. So kind of final thought on the whole idea of a log loss function. So I mentioned, our goal with this is to minimize this, right? We want to minimize the amount of loss in our model. Is it always the best idea to minimize the loss function? Obviously no. And you guys on the chat, Dean and John kind of throw it in there. It isn't. And we talked about that last week, right? Oftentimes we're concerned about overfitting. If we sort of overtrain our model, just focused on minimizing the loss, we can lead to a scenario where we overfit on our data. And that was where the idea then that we have to regularize it. So remember this beautiful little Elasticsearch there. So here we have our little loss function. In this case, it's an MSC thing. And then we have our little regularization term. So we have our L1, our L1 and our L2. So again, just to kind of recap, loss functions, it's how we keep score. And it's how our model sort of determines when it has kind of developed the best possible model of the data it has. And again, most models, except things like KNN where there's no explicit learning steps, but most models will leverage some kind of loss function to determine when they have kind of achieved that optimal parameter. So let me pause there. Let me just kind of take stock. Any questions on that? Okay, so I have already bored you all into a state of comatose submission. Awesome. Let's tee up sort of the next part of this thing, because I mentioned that there were those two things. There was the loss function and the optimization function. So now we have our scoreboard, right? We know if we're doing well, and we also know if we're not doing well. But now the question is, how do we sort of how do we kind of systematically approach testing values in a way to kind of get at this optimal solution, right? We have a way of keeping score, but like, how do we sort of approach it in a systematic manner? Do we literally just kind of throw random values at our weights and just kind of see what the loss function is, and then survey a billion different permutations, and then whatever one happens to be the minimum, we take that? Like, is that the approach that we're going to take to this? Or is there maybe a systematic approach that we can take to doing this? And what do you guys think? Is there maybe a systematic method that we can take? Okay, spoiler alert, there is. And that is the optimization. Right? Yes, that is exactly what a gradient descent does. It's a systematic approach to it, to kind of solving what this, minimizing your loss function. But before we get to the gradient descent, we will cover something else. We're going to first cover something called coordinate descent. So here's the intuition of this. I have this, let's use the example of logistic regression. I have that quadratic form where I have all my features and I have my associated weights. And for each of those weights, I'm going to try to fine tune it. Right? I'm going to try to kind of fine tune those. That's what I'm trying to do to sort of achieve that sort of minimized, that sort of minimized loss function. So if you take that notion of a fine tuning, let's essentially do that. Let's take each feature in isolation. Let's fix all the other features. Let's fix, x2 through xp. Let's just take our first feature, w1 associated with x1, and let me just fine tune it. Let me train on that specific thing along that specific axis. Let me find the associated minimum with that. Once I find that minimum, let me lock that down. And then let me shift to the next one. Let me shift to W2. And with all my other features locked, let me then, over sort of an array of training data, let me try to find the minimum value for that. When I find that, let me lock that down. Let me sort of do that systematically. And there's kind of a cyclical element to this. And this is kind of a key to how this works. Once I have finished iterating through all my features, I have to go back to W1. I have to say, okay, well, I set this as the minimum before, but that was when all my other features were weighted a certain way. Now they have all changed too. So now I have to see if this still makes sense. So now, keeping everything else frozen, I now try again to see if that's the minimum. If it isn't, I adjust it to the new minimum. And sort of if you know the expression like a round robin, you essentially do that. You can continue to iterate. You go, so in this example here, where I have two features, where I have features 0 and 1, and these are the weights, W0 and W1. I start along my W0, I find my local minimum for that, and then I kind of freeze that feature. Then I train for W1. I find the local minimum for that. Then once I've done that, I circle back to W0, W1, W0, W1, W0, W1, W0, W1, until, as you can see here, there's a point at which there's that diminishing return, where at that point I have converged upon my sort of minimum loss function value. So coordinate descent is this really, really conceptually simple model. And if it feels kind of not very elegant and a little bit brute forcey, it is. And by the way, for that reason, people kind of hate coordinate descent because they feel like this is dumb. We can do better. And you will constantly see people just trying to knock coordinate descent down and sort of come up with more elegant approaches. But one of the interesting things is that coordinate descent is actually a remarkably robust and efficient approach. I mean, there are downsides to it. And I kind of talk about that in this slide a little bit. But the interesting thing is that like it, even though it's simple and kind of dumb, it actually works really well. And which is why it is still in use very actively for this, for a number of problems. So that's coordinate descent. Any questions on that?
I have a question.
Mhm.
Yeah, so given that the problem is convex, are we guaranteed that coordinate descent will converge on the absolute minimum?
Good question. So I believe if it is convex, it will. So if you're looking at sort of a relatively simple, you're talking about essentially sort of a relatively simple convex like sort of, I guess,
Like a whole,
feature
yeah.
space. Yeah. If it's a simple thing like that, then yes, you're guaranteed that it will converge.
Okay.
Yeah. Where it starts to get into problems is precisely where it isn't necessarily convex. And then you need to, maybe, I mean, there are, just like with gradient descent, there are tricks that you can do for this. And we're going to talk about some of those tricks, but yeah, it is guaranteed to converge in the event that there's kind of a simple convex convergence. And just so you guys here, let me just kind of jump ahead and visualize what he's talking about here. But so if you imagine this as sort of a graph of your loss function, where you have all your different features in feature space, and you have the associated loss function with it. So there's the idea that like that point right there is going to be your loss. There's going to be sort of the minimum loss function value. And then there's going to be associated set of weights associated with that. And so it's the idea that like, so he's asking like, if you have a nice kind of simple convex type thing here, if you sort of initialize your weights there, will it be guaranteed to converge there? And the answer is yes. So that's what that question is asking. F is not well behaved. Yeah, so that's exactly where the question of like where F is not well behaved. We're gonna get to that in a moment, but like when your function looks more like this, and we're gonna talk about that a little bit, but coordinate descent does not necessarily handle those as well. Things like gradient descent are a little bit more robust for those. Yeah, okay, great question. Okay, so let's sort of think about another intuitive approach. If that seems, if coordinate descent seems effective, but a little bit brute forcey, let's talk about maybe a slightly more elegant approach that you can take. So intuitively, I have my loss function. I can plug in values. I can get an associated loss with that. But if I have that function, is that the only data I can potentially extract on not only my performance at that level, but maybe in my trajectory? And shockingly, no, there is obviously more information implicit in that. And that's specifically if you take the derivative. Take the derivative, then you're looking at the slope. You're looking at the trajectory at that point. You're not just looking at the value, but you're looking at how it's sort of changing and how it's shifting. And so that sort of tells us if we take that derivative, if we take that thing, we can kind of look at that gradient. We can look at the direction in which this is kind of shifting. And then based on that, because we can kind of look at in our different, like our n-dimensional space, we can figure out the directionality of the highest gradient, which is the steepest slope. We can say, okay, that's the direction we need to go in. Right? Intuitively, if I'm at this point here, I can see my slope on this axis is going sort of the furthest down. So I need to kind of move in that direction. And that's kind of the way I'm going to do it. And so let me jump ahead because I will totally edit useful content out of my slides for a meme. So, if you have intuitively, if you have initialized at this point, you can kind of assess the slope at that point, recognize that the maximum slope directionality is along that trajectory, then advance along that rate. And you advance, you advance, you advance, you advance, you advance, you advance. And then you can kind of see something happening as you get closer to the bottom. What happens to your gradient? What happens to the slope? It begins to zero out. It begins to flatten, right? And ideally, at some point you reach that bottom. At that point, the slope is zero. And that's what we mean to say that your learning model has converged. Because that kind of gives you a sense, right? Not only do you have your value of your loss function at that point, but because the slope is zero, you're essentially saying, okay, that's the best I can do. I've hit that bottom, I've hit that minimum value. So that's the notion of it converging. Did I cover this? Okay, cool. Yeah, okay. So Daniel, great point about local versus global. We're gonna run on that in a minute. One thing that I wanna mention here, if you'll notice with this really handy GIF here, you will notice that it's not a continuous descent, right? We take jumps. There's kind of a discrete sort of jumping step in that. And that's our learning rate. It's the idea that if we know the direction we wanna move in, there's a certain magnitude that we're going to take that jump to, right? There's no point, if we know that we need to go here, we know that our gradient is steep, we don't have to sample continuously along that. We can kind of jump ahead. And that's the learning rate. And one of the kind of the cool and interesting things that we're going to kind of explore here is the idea that this learning rate is something that can be optimized and something that can be manipulated. And you can kind of see this here too, right? There's this Goldilocks element to learning rates as well. So, too large, and you may get a scenario like you see down here, where instead of hitting that absolute bottom, we reach a certain point, and then instead of like continuing down it, we kind of begin to bounce around. Too small, and you get into a scenario where the computation becomes intractable, because rather than advancing in a sort of an appropriate clip, you kind of get stuck slowly moving down your gradient, and you never actually kind of hit a convergence. And so, one of the things that we kind of touched on with project 2 that hopefully we're going to give you a little bit more context around is this notion around max iterations. So it's the idea that you will allow your model to run, but at some point you're going to stop it. At some point, either it has been allowed to fully converge, or if it hasn't, and when you set your max iter to 10, you've essentially said, I'm going to only allow this to update 10 times. And surprise, surprise, your model has not fully updated. Your model has not fully converged in 10. After 10 kind of updates, then it'll give you that warning, say like, hey, maybe your model's not really doing the best thing it can do. The last thing I'm going to note about learning rate, which is kind of one of these cool techniques that you could do with it, is you can make it adaptive. It doesn't have to be a fixed value. Now, one of the things you're going to see with one of the particular methods we're going to explore is it does precisely that, where when the gradient is very steep, it says, you know what, I know I'm nowhere near the minimum. So you know what, I'm going to do a really large learning rate because I'm going to take a larger jump. But as I get closer and closer to the bottom, as my gradients start zeroing out, then I know I need to be a little bit more precise. And so then my learning rate kind of also shrinks. And that's kind of another really cool modification you can do to your learning rate. So now this is the next thing, and this is something that kind of Daniel hinted in the chat. Up until now, we've been dealing with these nice, beautiful kind of convex bowl-like structures where I can just initialize anywhere in this, and my model will just naturally work its way down to the minimum, and everything is happy. The reality is that is almost never the case in real life, and particularly when you get into sort of larger, more complicated models, this can become very difficult to sort of address. And you can see here the difference between sort of a local and a global minimum here. So, here's a local minimum. It's our little, I'll use the metaphor of a pothole. It's our little sort of dip, our small little valley there. But the reality is we don't really want to end up there because our performance there is suboptimal. What we really want to end up in is this global minimum. And what you can see here is that in this case, where you initialize could have a huge impact on where your model ends up converging. And so, if I happen to initialize here, well, then great. I'm just going to go right down here and I'm all set. But if I converge here at point A right here, my model is going to converge me there. I'm going to say, well, I've flatlined, I've hit my minimum, everything is good. And so clearly that is problematic. And by the way, this is sometimes why. So, one of the things that you might ask is like, why would the same data plugged in the same model sometimes give me vastly different results? And this might be why. Because you may initialize your values arbitrarily, you may end up initializing in a very different region of your loss function, and it may converge on a different minimum. So yeah, it's problematic. And this, to give you kind of a sense here, I found this example. This is a representation of sort of what the loss function for a 56-layer convolutional neural net looks like. This is obviously not the actual loss function because the loss function is in n-dimensional space, but this is sort of a representation in 3D of what a loss function might look like. And just to kind of give you a sense on just how convoluted and how challenging it can be for your optimization model to actually find a global minimum in this. So yeah, it's challenging. And one of the things that we kind of have to struggle with is to think about, okay, well, are there approaches that we can take to maybe be a little bit more robust in sort of arriving at a global minimum, or at least something closer to it? So there are different approaches we can take to this. And if there is just one ongoing theme of this course, it is options. Your menu of options expands. There's actually, quick aside, but in behavioral economics, there's actually a well-known concept of decision paralysis and decision fatigue, where if you're presented with too many options, it can actually be stress-inducing. And there's actually sort of an optimal number of options that sort of people are comfortable with. And if you sort of overdo that, you can actually sort of create sort of an inferior experience. And so you see that a lot with things like menus and things like that. Like people like a few options, they like the idea of being able to choose, but they don't like being overwhelmed with stuff. So I mentioned that in that context because, boy, doesn't it feel like we are just getting into decision fatigue here when it comes to data scientists. But yeah, so some things that we can do here. And one of the biggest steps that we can take is being a little bit anarchic, a little bit messy when it comes to our approach. Right? So if you think about, the plot that we had here, we had this nice kind of smooth thing here. We initialized, we went down, we converged. It was great. It was smooth. Everything worked well. Now we're going to say, let's try to be a little messier. And let's see if in the process of being messy, we can kind of avoid the pitfalls of converging a little bit too early, a little bit too quickly in a suboptimal result. Two options that we can take for that. The first is how we calculate our gradient descent. And I'm going to talk explicitly about what that means in a slide or two. But if you remember, what I said was that we updated our learning rate at discrete intervals. We said that there was, we would kind of plug in some numbers, and I was vague on that, and then we'd get a result, and based on that result, we would update. So we have options, yet even more options, about how often we do that updating. And specifically, we have the option as to whether or not we want to update it for every value in our data frame. So, if you think about like each row as being a unique value, we could theoretically update our value every time, or we could do it after we've done sort of a batch. So rather than doing it each time, maybe we run a series of values, a series of rows. And then depending on the performance of that, and we average the performance based on that, we do an upgrade. So generally speaking, if you tend to sort of do what's known as a stochastic approach, which is you update it every time, that will tend to kind of lead to a lot more chaotic results. Because if you think about your performance, one value may indicate that your performance is maybe trending in this direction. Then you may get an outlier that will say, oh, actually, you're in a completely different area of your loss function. You are way over here, and you need to update accordingly there. And then you'll get another one, be like, no, actually, you're over here. Whereas if you do sort of a more batched approach, where you take averages over time and then update based on the average performance, you'll get less of that sort of variance. And so it'll be sort of more of a smoother convergence down. So that's one kind of approach we can take to this, which is, again, doing the kind of the batched versus the more stochastic approach. The other thing that we can do is going back to our learning rate. And I kind of hinted at this earlier. So remember here when I said your learning rate is too big, and if it's too big, you can kind of just bounce around and never actually converge. Well, the flip side of that is if your learning rate is big enough, you can theoretically jump sort of over these smaller potholes. So the metaphor I give here is like, if you think about your local minimum as potholes, you want a learning rate that's going to kind of ignore those. It can just roll over those and be like, that's not useful for us. We don't care about that. We can do a lot better, right? We want to get stuck in the actual ditch that is the global minimum. We don't want to be stuck in some little pothole there. So we make our tires big enough, we make the learning rate big enough, and can theoretically jump around until we've theoretically hit the big ones. So those are some approaches we can take for our learning rates. And And that leads to this. And oh, by the way, I love this photo. One of my finer parenting moments. But you can kind of see here, we run the gamut about some approaches that you can take to this. On the one extent, you have your batched approach, which says, let's run through our entire data frame. Let's average the performance against our entire data frame. And then based on that performance, we then update. And so every update requires that you process your entire data set and see the results. And there's a trade-off with this. It's computationally efficient because you tend to perform fewer updates to your learning model. But as we said, there's an inherent stability to it. Because it averages out, it tends to smoothen your gradient descent. You're not bouncing around. So again, there's that trade-off there, right? The flip side of that is your stochastic approach to gradient descent, which says literally plug in every particular row, every particular instance in your data set. And then based on how that goes, you then update each time. And it's essentially the exact inverse of your batched approach, which says that, okay, you will tend to converge faster, because your learning rate is after every time. It's not after running your entire data set. And you also get kind of a more granular sense of how you're improving. But again, it's more computationally expensive. It tends to be more noisy. And you don't always get that kind of consistent performance of descent. The third approach to this, which is kind of taking a hybrid approach of these two, says, you know what? Let me try to take the best of both worlds. And that's the whole idea of a mini batched approach, which says, rather than running through my entire data frame, let me just take a segment of it and let me average that out. So I'm still getting a bit of a stochastic element, but I'm also getting I'm also kind of getting a little bit of a kind of a batched smoothing effect too. So just some examples of approaches that you can take to sort of your rules for updating your gradients. Okay, let me pause there, because I think that's kind of giving some sense there. Hopefully this kind of gives you, I guess, a little bit of an intuition to how an optimizing function works, and some of the sort of the knobs and the levers that you can kind of pull to sort of manipulate the performance of your optimizing model. So, okay, so there's a question in the chat about why SGD is more computationally expensive. So it's more, so there's a little bit of a trade-off if you want to think about this from a computational perspective. The a batched thing is you have to sort of plug in more values, but right, because you have to go through your entire data frame, but you're updating your learning model and you're recalculating the weights fewer times. The flip side is with a stochastic one, you're obviously, for each model, you have to go through and recalculate the weights and then the associated gradients with it. So there's a little bit of a trade-off computationally, but that's the cost for that. Every time you update those weights, you then have to recalculate the gradients associated with it. You have to solve for the new weights, and you have to solve for the updated gradient. Yeah, I know, but no one's getting GPUs these days. Cash in all your Dogecoin, get yourself some GPUs. All right, so we feeling that? We're feeling good with that? Okay, cool. Let's talk about some specific examples, because we touched on in project 2, we kind of touched on a couple learning models. We specifically touched on liblinear and we touched on SAG. So I wanted to kind of mention both of those explicitly. So liblinear, going way back when to the top of our thing, is an example of a coordinate descent algorithm. And so it's really good for kind of linear classification models. And because you treat sort of each coordinate, each vector independently, it is something that works really well for that. One thing that's kind of cool about this is that one of the things, so you may notice for liblinear, we had to set liblinear and then we had to set the penalty to L1. And part of the reason for that is that a liblinear only works with an L1 regularization. I'm not entirely certain why the mechanics are for that, but one of the results of that is it uses L1 to apply automatic parameter selection. And I wanted to flag that because I think that's something we're going to ask you to do in project 3. And I know I should have looked at the prompt because I keep telling you guys to do that, and I should have done that myself, but I know we were talking about doing that. But one in the ways in which you can sort of prune your feature selection is by applying L1 regularization, right? By zeroing out certain features that just aren't as important in terms of your performance and your loss function. And so liblinear does that. And by applying L1 regularization as part of the liblinear process, it does that automatically, which is kind of a cool thing to note about a liblinear approach. As a result, when you look at like the recommendations for it, so maybe when you were looking at the documentation, you may have noted that like it will tell you it's really good for solving large scale classification problems. So when you have very high dimensional data sets where you want to do that pruning, you want to do that parameter selection, it's really good for doing that. So that's the first model we sort of had you explicitly play around with, liblinear. The second one, SAG, which obviously stands for the Screen Actors Guild, is also this like really, really cool idea. It's this really, really cool approach that, you know, when we talk about like adaptations that you can do to like a stochastic approach, this is it. So the first thing that it does is it works like a stochastic gradient. It converges, finds a minimum. Then what it does is it caches that minimum and the associated values with it. What it then does is it sort of, and I remember how I said that you can sort of make the learning rate adaptable. It then sort of jumps the learning rate up to basically have you like jump out of your minimum and you end up sort of somewhere else randomly, and then you converge again and you save that value. And then you jump out again and you sort of converge on a new thing and you save that value again. And then it uses the performance against all of those sort of local minimums to try and direct the positions in which you jump. And so the way to think about this is to say, you know, yes, it's really cool to kind of see when you're at a point which direction you should be going, but it would also be cool to see like within a region, are you heading in the right region? And by sort of caching all of your local minimum values, you can say, well, am I trending in the direction that, you know, things are going down? Am I approaching something like this where maybe the global minimum is? Or am I like trending in this area where actually my minimum values are increasing? And then you're able to say, oh, you know, actually we want to, when we take that hop, we want to actually go in this direction. So we want to converge down that direction. So it kind of gives you this really, really cool sort of meta view of within your convergence rate, like, are you doing that in a way that's kind of approaching more of a global thing? So I just think it's a really, really cool approach to it. So let's see. So wow, so I actually went through this pretty quickly, but yeah, so I guess final thoughts on this. So, you know, I think at this point, hopefully you're kind of getting the feeling of this. Maybe when you kind of start out in your depression, maybe there are like a few things that you can tweak here and there and get your thing. And hopefully what you're kind of beginning to realize is just the sheer volume of options and permutations and kind of features that are available to you, and really the kind of the daunting element of it. Everything from, you know, early on in the course when we were focused on the data engineering component of it and how you could kind of engineer your different features, to now the selection of your loss model, the selection of your decision boundaries and your thresholds with that, and to now your optimization functions and what kind of parameters and approaches you can take to sort of arriving at an optimization solution. So like, hopefully you're kind of beginning to see like there's a lot of options available to you, and kind of bringing it back full speed. That's why, you know, I mentioned it's the kind of thing where the threshold to do data science is very low, but the threshold to do data science well is very high. because there's just so much here to kind of dig into. So that's, I think, what all I had for today. That's all I really wanted to talk about for today. So let me open up to you guys. Questions, comments?
I did have one question, which
Mhm.
also made me realize that I think my mic's been unmuted the whole time. So sorry if I hope I didn't make any weird noises. So couldn't you also have like a situation where you have like a, I mean, the best way I can think to describe this is like, say you have a hill and you have a well in the top of the hill, and the well takes you to your global minimum. So like in order for you to get to the global minimum, you actually kind of need to go to the highest point. Does that make sense? And
Mhm.
all the other areas would be leading you away from where you actually needed to be.
Yeah. So the short answer is yes, absolutely. And the longer answer is that that's why this is kind of an ongoing challenge. It's really sort of, it's non-trivial, particularly, it's easy enough when you're dealing with simple models and relatively simple data sets, but as you get into the deep learning type models where you have these super, super complex and convoluted loss functions, arriving at a global minimum and doing it in a computationally tractable manner becomes incredibly difficult, right? Because it's easy to just visualize a loss function and say, oh, well, look, just head over there. But in actuality, from a computational standpoint, it's just incredibly difficult. And there's so many approaches when it comes to like, I haven't even talked about some of the approaches, but like one of the things I mentioned is that you have arbitrary starts. Well, another approach may be to kind of do employ optimization function, but do it in like a somewhat systematic way. Or try different arbitrary start values used to try and see like where your model converges within that space. But yeah, I mean, this is an ongoing, like if you want to, if you want to like where the researchers, like where the people working on machine learning are working, it's precisely in problems like this. How do you efficiently arrive at a global minimum when you're dealing with such complicated sort of loss function space? Because you're right, there's no method that I've described that will guarantee you that if a global minimum exists, it will converge on it.
Okay, thanks.
Yeah, absolutely. Okay, any other questions? And that is awesome. I guess I will stop the recording early.